Okay, I want to share the solution of this Dota2 Senate problem. Uh, but so I've already solved it. I'll explain it in my own words. Here, the description is it's a little too long, and it has a story, a Dota2 game, and something like that. But it basically, at the end, we have to return a radiant or die, and I'll explain it in my own terms. Let me go here. You're basically given a string. A string consists of uppercase letter R and D. R and D, let's say they represent characters in a game. So we have currently a string of these letters R and D, and every R has the right to eliminate, completely remove a D, and every D has the same right. I mean the same right, like to remove R. So basically, let me give you an example. This R can remove one of these D's, and this D can remove this R. So R removes D and D removes R. This is basically the game, and the game will end when in the string we have only one type of character. We have only R's or we have only D's. And if we have only R's, the winner is Radiant, and otherwise it's Dire. So in the original description, if we go back here, it says the wording for this change. There's a game, and there must be a change on the Dota 2 game. It doesn't really matter. So the wording for this game is a round-based procedure. It says the round-based by round-based procedure, they mean that. Let me demonstrate it with an example. In fact, there is an example. Let me do it here. So we start with an R. R removes this D. By removes here, it's officially banned. So banning basically is removing. So we remove this D, and then we skip this D because it's removed, and then this D removes this R. So then we go back. So the first round is done. So we go back to the first one. This is already removed. This is already removed, and then we go back to D. Now we can see that we only have one character, which is D. So the game ends here. The winner is Dire. Let's take another example. Let's say we have D, D, R, R, and R, and we start from here, from left, and this is the first round. In the first round, this D removes one of these R's. Let's say you remove this one, and then we move to the next D. This D removes another R, which is this one, and then we skip this R, then we skip this R, and then now we're here. This R removes one of these D's. It removes this one. So the first round is done. After the first round, the two characters that remain are R and D and R. So this is our current string. And then we start the second round. And the second round, we start with the D again. D remove this R, and then we go to the R. The R is removed. And now the second round is done. And at the third round, we see that we only have D. The string contains only one type of character. So we stop at this point. The winner is Dire. So you see, it says the round base. It's the round base procedure. But we can actually think of this as a circle because we're not asked about anything about the rounds. We're never concerned about the rounds itself. We're only concerned about the removal. We're only concerned about the procedure. So we can think of it as a circle. So there is from this point on, there will never be anything about the rounds. It's just a circular process that continues until all of the characters in the string are same. So if we look at this like that, D, D, R, R, and R, and we're initially given a starting point. This here, and after that, we'll never have a starting point. It just goes on and on. So in the clockwise. So this D removes this R. So then we move to here. This D removes this R. And we skip this one, we skip this one, then we're here. This R removes this D. and then we skip this one. This D removes again the next R. These are already removed. So this, and then we go back to here. We have only one D standing. So this is a circle-based one. It makes sense to think of it as a circle-based one. And what you need to do in this problem is that we can think of it, if we do it a circular way, if we can start from the beginning of the string. We don't have to have a circle though. We can have the string. As we remove the elements, we'll just mark them with some special character so that we can skip it. I use the dollar sign in the code, and I'll explain it. So as we encounter a D, let me explain it another way. Let's say we encounter a D, and there are some other characters. What this means, before this, there might other characters. This D can potentially be removed if there was an R before it that was not being removed, because this R has the right to remove it, has to eliminate. If there was an R to remove this D, then we remove it and skip this one. We don't do anything. Otherwise, there were no R's, so this D has now have the right to remove an R after that. So that's why we'll have two counters. So we'll say remove count. We'll call it remove count R, which means that how many R will be removed, and remove count D, how many elements. If at some point, if we reach a D and remove count D is greater than 0, that means before this there were some R's. There could be one, or if there are like three R's, there will be this is going to be equal to 3. Of course, this R's should not be removed ones. We don't care about the removed ones. There may be some R's that were removed by other D's. We're not concerned about this R's. So, but this R, for example, so this will remove this R, this will remove this R, and this R will remove this D. So that's why we increase it by 1. So when we reach this D, we'll see, okay, count D is 1. That means there was an R that was not being removed. So it has to remove this R, this D. So we remove this D and skip. Otherwise, it has the right to remove an R after that. And so there's somewhere after D, somewhere at this point, let's say we have an R. This D can remove this R. So in case that we don't remove D, we increase the remove count R, because it can remove some R, potentially some R's. So how I did that in the code. So every time, and how we'll determine that we have only one characters. So this is pretty simple. If we have initially we have some number of R's and some number of D's, and every time we eliminate some D, we'll decrease the number of D's, and every time we eliminate an R, we decrease the number of R's. And at some point, if one of them equals 0, then that means we have only the other character. So that at that point we stop. And later I'll talk about the time complexity, but let's see the code here. And I have count R and count D. This shows the number of character R and D in the initial string. And this was just an example. And then we have remove count R and remove count D. And every time remove count R increases when we see a D character that is not removed, and remove count D increases when we see an R character that is not removed. And as long as count R is not 0 and count D is not 0, that means the game does not end. We need this modular operation because we initially have a string. So when we reach the end of the string, let's say like this, and I goes like this, and it goes one index beyond the length of the array. So that's why we take the modulo. It wraps it around to the first index. It's like that's why it behaves like a circle. So then if we check if Senate I is removed. Previously, we don't care about this. It's already removed. We're just going to increase I and continue to the next character. Otherwise, it's not. If it's not removed, we see, okay, is it D? So it's D. And if you remove count D is greater than 0, so that means there was previously an R. So this R eliminates this D. So that's why we eliminate it. So we mark it with the $sign and remove count D decreases. Now we have one less character D to remove, and count D decreases. This is the number of characters initially in the string. Okay, and otherwise, if we don't remove it, this means that this D itself can potentially remove an R. So we have remove R count increases, and this is similar for the character R. And then we increase at the end the index to the next character. And at the end, we check if count R is in 0. So that means Radiant wins, and otherwise Dire win. But what is the time complexity? First, let's check out the constraints. Okay, we have n at most 10 to the 4. So you might guess that it's either at most n squared or n log n, or maybe we can have a linear time complexity. So the worst that you can do is O of n squared, a quadratic time complexity. In fact, this is quadratic in the sense that in every iteration we remove at least one character. Why? Because if we don't remove at least one character, when do we remove a character? So if we remove D, that means there's an R. If we remove an R, that means there's a D. If we don't remove a character, that means all of the characters are same, because R cannot remove an R, or D cannot remove a D. So if we don't remove a character, the while loop stops, it terminates. If we remove, so that's why if while loop continues, in every iteration we at least remove one character. So for example, in the first iteration, if there were n characters, in the next iteration there will be at most n minus 1. And in the next one will be n minus 2 and n minus 3, all the way up to plus 1 or even 0 at least. So if we sum this up, it's at most of n squared. So that's the time complexity. If we have 10 to the 4, so if you have 10 to the 4, you can do a of n squared. This is pretty much the limit. If you have 10 to the 5, that's it. You're in a different territory. You have to think about of n log n, of n log n, or maybe n log n squared, or maybe something with the square root of n times n. Maybe it would work, but not O of n squared anymore. So that's basically the code. I just want to show you completely if you want to see how I did that. So I hope you understood the core logic. Now honestly, this problem statement is too long, and what it says is a little confusing at first. Yeah, it's just a story. It doesn't really matter. You have to change it to your own, according to your understanding. So yeah, that's basically it.